Assalamualaikum, my name is Muhammad Aminuddin Ahmad Zaki. My matric number is CD250111. To talk about introduction. Wall mounted workshop jeep crane are commonly used in factories, assembly lines and workshops to lift and move heavy material. They are attached to the wall or steel column, which help save floor space and improve work efficiency. The crane consists of a horizontal boom, a diagonal support rod and a movable hoist. When lifting heavy things, the crane experiences bending and axial force that creates stress in its structural component. The highest stress occurs when the hoist positioned at the far end of the boom. Therefore, the study analyzed the loading and stress distributed of the crane, evaluate its safety based on ASTM A36 steel properties, and determine the factor of safety to ensure safe operation under maximum loading condition.
Assalamualaikum. My name is Ahmad Amin Zafran bin Zainal Abidin. My number matric is CD250060. I will present about literature review. This literature review discusses the fundamental engineering principle used in the structure assessment of lifting machinery, such as workshop cranes. First, normal stress is calculated using the equation sigma equal P over A, where P represents the applied axial force and A is the cross-section area of the structure members. The stress may occur as either tensile stress, which stretch the material, or compressed stress, which shorten it. Next, the crane structure must satisfy the condition of safety equilibrium. This means that the sum of force in both the horizontal and vertical directions, as well as the sum of moment, must be equal to 0. This condition ensures that the structure remains stable and does not experience unwanted movement or rotation. In terms of material selection, ASTM A66 steel is commonly used for the crane components because it provides good strength, ductility and reliability performance under the heavy loads. Finally, the allowable stress is determined using the factor of safety, or FOS. This ensures that the working stress remains below the material safe limits, reducing the risk of structural failure and improving overall safety and during operations.
Hi, Assalamualaikum. My name is Muhammad Amirul bin Azman and my matric number is CD250126. So I want to present to you about problem definition. So this is our wall mounted jeep crane. Its purpose is to handle heavy lifting in a tight space without taking up any floor area. The design is simple. The boom is the horizontal arm that carry the load. So the second one is the tie rod, is the angle support bar that connect to the wall to hold the arm steady. Because of this triangular setup, the crane is incredibly strong. When we lift a load, the weight is safely transferred into the wall mount. So we keep the design safe by using high straight steel and strike weight limit, ensuring it's stable no matter where the arm is positioning.
Assalamualaikum, my name is Muhammad Haziq bin Muhammad Akmal. I'll be continuing our video presentation. So let's move on to mathematical model. So the first is the configuration, which is basically overbraced wall mounted workshop jeep crane. The assembly is via horizontal jeep arm supported by an angle structure tie rod. So the idealized model is a 2D pin joint truss frame hybrid system. So the load application combines a moving point load and uniformly distributed load. So what is the structural simplification? The horizontal member is treated via Euler-Bernoulli beam theory. So this theory refined as plane sections remain plane after loading. section remain perpendicular to the longitudinal axis, and transverse shear deformations are neglected.
Assalamu alaikum everyone, my name is Umar Farouk Tariq. My matric number is BD24003. Today I would like to continue our presentation in the discussion area. First, I will talk about the core finding and the stress behavior. Our analysis confirm a fatal truth in a cantilever beam. The action happens at the support. Maximum stress always occur at the wall connection, the fixed end. Why? Because this is where the bending moment is at its peak, while the free end of the beam might move the most. It is the connection of the wall that carries the heaviest burden. The mechanical principle. To understand this scientifically, we look at the normal stress formula. The stress equal to the moment multiplied by the distance over the second moment of inertia. The theory versus reality. However, we must acknowledge the real-world deviation in our calculation. We assume a perfect rigid support and a homogeneous material. In reality, factors like weld quality, bolt tension, and wall flexibility can lead to deviation from our ideal models. Theory gives us the map, but the physical installation determines the journey, the challenges, and scope limitation. It is important to note the boundaries of this study. To ensure clarity, we focused strictly on static loading. In a real environment, factors like dynamic impact, wind-induced vibration, and material fatigue play a massive role, while our current model provides a strong foundation. A full finite element method analysis would be the next step to account for these complex variables. Design improvement and application. How do we improve this system? First, the geometric optimization. Increasing the cross-sectional area directly lower the bending stress. Second, the deflection control. Adding a diagonal brace is a game changer. It transfers the bending moment away from the wall connection, turning a positional point of failure into a stable triangle. Safety factor. We always apply a robust factor of safety (FOS) at the connection point to handle unforeseen stresses. In conclusion, this cantilever beam is a versatile tool. We see it in industrial shelving, lifting brackets, and massive agricultural overhangs. By mastering the relationship between load, geometry, and support, we can build structures that are not only functional but exceptionally safe. Thank you, everyone.
So the next one, I will present about results. This project focus on structural analysis of wall mounted jeep crane design to maximize floor space while providing a 180-degree lifting range. So using a 3-meter boom and 1-meter bracket high, our geometry create an 18.53 degree tie member angle. The system was designed to handle a load of 12.76 kilonewton using a UB 203 multiplied with 133 multiplied with 25 S275 steel beam. So our analysis of the internal force undefines a maximum bending moment of 39.41 kilonewton meter and significant tensile and compressive force of approximately 40 kilonewton each in the supporting member. By calculating axial and bending stress, we determine maximum stress of 115.51 meter Pascal with allowable stress capacity of 269.30 meter Pascal. Our safety certificately result in a factor of safety of 1.59, confirming the design of structurally sounds for its intended use. Thank you.
conclusion, this study successfully analyzed the structural loading and abnormal stress distributed of the wall mountain workshop jib crane. The analysis showed that the horizontal boom experienced compression and bending stress, while the support tie rod mainly experienced tensile strength. The wall connecting was identified as the most critical part of the structure because it is subjected to the highest bending moment. Based on calculated stress and safety evaluation, the crane is able to safely support the design without exceeding the material elastic limit. The result can also be used to improve future crane design and enhance structural efficiency.